So, Electrochemistry chapter. We are going to, under this chapter, we are going to learn three important aspects. Number one, about conductance and related concepts and related terms. Okay. Then second one, we are going to discuss about electrolytic cell. Electrolytic cell. Under electrolytic cell, very specifically, we are going to discuss about electrolysis. Okay, what is electrolysis and how to identify product of electrolysis. Then third part is about galvanic cells. Galvanic cells. Okay, so these are the three important parts that we are going to discuss under electrochemistry chapter. Okay, so let's begin with the conductance first. Yeah, so I'll introduce the first term, resistance. Resistance, which is denoted by the symbol R. Resistance is denoted by the symbol R. What is meant by resistance? Okay, of a material, right? Your material may be a solid or maybe a liquid. Okay, so what is generally resistance? Resistance is the ability of a material. Is the ability of a material. The material may be liquid or may be solid, whatever it is. Resistance is the ability of a material to obstruct or prevent. Let me write the word prevent. Okay, is the ability of a material to prevent the flow of charge. Prevent the flow of charge through it, through the material. Okay, through it. Is the ability of a material to prevent the flow of charges, right, through it. This is what we call as resistance. Okay, so the material itself provide some obstruction, okay, to the flow of charge through the material. This is what we call as resistance. Okay, and resistance, we go to the next page. I am going to give resistance in terms of electrolytic cell. So let me take a solution in a beaker or in a vessel. Okay, we have some solution. Now I'll immerse two electrodes here. Two electrodes. Okay, I'll connect one to the negative terminal of the battery and another one to the positive terminal of the battery. Okay, let the distance between the two electrode is L. Okay, and let us assume that the electrodes are not moving. I'll immerse the electrode completely in the solution. Okay, so this is one electrode and this is another electrode. Let us assume that the electrodes are not moving. Okay, the distance between the electrode, right, is nothing but L, and the area of cross section between the electrode. Okay, there is some area between the two electrode, and that area is what we call as area of cross section, which is denoted by the symbol A. Remember, resistance of this solution, I have told you, the material may be solid or may be solution, right, whatever it is. Resistance of the solution is directly proportional to L and inversely proportional to A. Okay, this is a fundamental relation. People have identified this. Resistance is directly proportional to L and inversely proportional to A. So if we increase the length of a if we increase the distance between the two electrode, automatically resistance will increase. Okay, if we increase the area of cross section, then resistance will decrease. Students, observe carefully. Right? If you increase the distance between the two electrode, resistance will increase. Whereas if you increase the area of cross section, okay, if you take larger electrodes of larger surface area, definitely the resistance will decrease. Okay, this is the basic relation, okay, for resistance and the distance between the electrode and area. Okay, if I equate this then we should introduce a constant. Okay, that constant is given a symbol called rho. R is equal to rho into L by A. Okay, what is this rho? This rho is nothing but specific resistance. This rho is called specific resistance. Okay, some people call this as resistivity also. Resistivity. Specific resistance, also called resistivity. It is basically proportionality constant. Okay, student, can anyone tell me how will you define?
Yes, sir.
Yeah, so rho is equal to R into A by L. This is the relation for specific resistance. What is specific resistance? If you keep L equal to 1 unit and A equal to 1 square unit, then whatever resistance that is offered by this material, okay, whatever resistance that is offered by the material is nothing but the specific resistance, also called resistivity. Okay, now we'll see what are the units of these resistance, right, and specific resistance and all. Unit. What is the unit? Resistance is given an unit called ohm. Ohm is the unit of resistance. Student, note down. Ohm is the unit of resistance. In chemistry, we often write it as ohm, but in physics, okay, you might have used this symbol, okay, omega symbol, that is also called as ohm, right? This is the unit of resistance. Okay, what is the unit of specific resistance? Rho. Specific resistance rho, you know very well, rho is equal to R into A by L. Unit of R is ohm. Unit of R is ohm, and in the numerator we have area, in the denominator we have length. Okay, area is in SI unit it is meter square, and length is meter, so meter square by meter is meter. So the unit of rho is ohm meter. Note down. Resistance unit is ohm, and specific resistance unit is ohm meter. So what is specific resistance? Very simple. If you take a solution, right, if the distance between the two electrode is 1 meter and the area of cross section between the two electrode, instead of meter we'll say like this, if the distance between the two electrode is 1 unit length and if the area of cross section is 1 square unit, then the solution present between the two electrode, students observe carefully, if the distance between the two electrode is 1 unit length and the area of cross section between the two electrode is 1 square unit, okay, then the solution present between the two electrode will offer some resistance. That resistance is nothing but specific resistance. Okay, specific resistance, also called resistivity. Students, keep this in mind. Resistivity is a constant for a given substance at a given temperature. Note down. Rho is a constant actually. Rho, it is not a universal constant. It is a constant for a given material. Okay, rho is a constant at a given temperature. At a given temperature, it will vary with the temperature, but at a given temperature is a constant. Rho is a constant for a given material. for a given material or solution, right? For a given material or given solution at a given temperature. Keep this in mind, very, very important. Right? Now, let me introduce the next term called conductance. 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 The common symbol that is used for conductance is G. G. Okay, conductance. Some people are using the symbol C also for conductance. Some people are using L symbol. Okay, so sign is not important here, right? Symbol is not important here, so keep that in mind. I am going to use the symbol G here. What is conductance actually? It is the ability of a material that allow the passage of charge through the material. Okay, it is found that conductance is inversely proportional to resistance offered by the material. Take down. Mathematically, conductance is nothing but reciprocal of resistance. Right? You can also write like this. It is the ability of a material that allows the flow of charge through it. Okay, that allows the flow of charge through it. This is the in this way you can define, but the mathematical definition is very famous for conductance. What is conductance? Conductance is nothing but reciprocal of resistance. Okay, so what is the unit of conductance? Very simple. What is the unit of G? 1 by R. Unit of R is ohm, right? So R is in the denominator, therefore unit of conductance is ohm inverse. Ohm inverse. But instead of ohm inverse, you can also use the unit mho. Mho is nothing but ohm inverse. Okay, but nowadays, students observe carefully, nowadays people are using another unit called Siemens. Siemen. Okay, so ohm inverse, mho, Siemen, these are all one and the same. Right? And this is the unit nowadays people are using S. S means Siemen. Siemen is the unit of conductance. Okay, any doubt, student, up to this? Any doubt?
No, sir.
Yeah, good. Now, we know very well R is equal to, okay, just now we discussed R is equal to rho into L by A, correct? Okay, we derived this. Now what I'm going to do, I'm going to substitute this R here. So G is equal to, I can write G equal to 1 by, in the place of R, I'll write this rho into L by A. Or I can write this as 1 by rho into A by L. Okay, 1 by rho equal to 1 by rho into A by L. Right? What is 1 by rho? Students, observe carefully. Rho is resistivity or specific resistance. 1 by rho, reciprocal of specific resistance, is called specific conductance. Right? 1 by rho, right, is called specific conductance. And we use a symbol for specific conductance. Specific conductance is also called conductivity. People call it as conductivity. Right? Symbol for conductivity is kappa. Symbol for conductivity is kappa. Okay. So I am going to replace this 1 by rho by the symbol kappa. So what is G? G is equal to kappa into A by L. Then what is kappa? Right here, then what is kappa? Kappa is equal to G into L by A. G into L by A. Okay, student, note down. Where kappa is called conductivity or specific conductance of the material. Specific conductance of the material. Take down. See, conductivity kappa is nothing but G into L by A. Okay. If I keep L equal to 1 unit length, and A equal to 1 square unit. Okay, area is 1 square unit, right? Then so if I keep L equal to 1 and A equal to 1, then I'll get kappa is equal to G, right? Under this condition, I'll get kappa equal to G. What is meant by that? Kappa is nothing but, or conductivity is nothing but, conductance offered by the solution, okay, present between two electrodes which are separated by 1 unit length, and the area of cross section between the electrode is 1 square unit. Okay, take note. So what is specific conductance? Specific conductance is defined as okay, is defined as the conductance offered by a solution. Specific conductance is defined as the conductance offered by a solution placed between two electrodes which are separated by 1 unit length, which are separated by a distance of 1 unit, by a distance of 1 unit length, and area of cross section of 1 square unit. Okay, so specific conductance is defined as conductance offered by a solution which is placed between two electrodes which are separated by a distance of 1 unit length, and area of cross section is 1 square unit. Okay, yeah, you can define in this way, or else you can define the other way also. Let me write in the next page. So what is conductivity? Just note down, student. See, the meaning is this. Suppose I'll take a solution. Students, observe carefully. I'll take a solution in a vessel and I'll immerse two electrodes. I'll connect one to the negative terminal, the other one to the positive terminal. Okay, students, observe carefully. The solution present between the two electrode, not the entire solution. I'm talking about the solution present between the two electrode. If the distance between the two electrode is 1 unit length, okay, L equal to 1 unit length and A equal to 1 square unit, then the solution which is present between the two electrode will offer some conductance that is called kappa. Conductance of the whole solution, listen, the entire solution will give some conductance, that is nothing but G. Students, keep this in mind. The conductance of the whole solution is G, whereas the conductance between the two electrode, if the distance between the two electrode is 1 unit length and the area of cross section is 1 square unit, then that solution, that is solution between the two electrode, that solution will offer some conductance. That conductance is nothing but kappa or conductivity. Okay, yeah, let me define in this manner. See, suppose if L is equal to 1 centimeter and A is equal to 1 centimeter square. Students, observe carefully. If L is equal to 1 centimeter and A equal to 1 centimeter square, what will be the volume of the solution between the two electrodes? Students, observe carefully. I have two electrodes. I kept the two electrodes parallel to each other. They are parallel. Okay, distance between the two electrode is say 1 centimeter, and the area of cross section between the two electrode is 1 centimeter square. 1 centimeter square. Now what I am asking is, what is the volume of the solution which is present between the two electrode?
1 centimeter cube.
Very good. 1 centimeter cube, correct? Right? So we can also define, therefore, volume of the solution between the two electrodes, right, is nothing but 1 cc, right? Also you can say that 1 centimeter cube. Cc means cubic centimeters, 1 cubic centimeters. Now listen, student. So you kept L as 1, A as 1, correct? Then 1 cc solution will give some conductance, correct? That conductance is nothing but kappa. So conductance offered by 1 cc solution is nothing but kappa. So you can define kappa in this manner. What is kappa? What is specific conductance or conductivity? It is the conductance offered by 1 cc volume of solution if L equal to 1 centimeter, A equal to 1 centimeter square. Okay, so if L equal to 1 centimeter and A equal to 1 centimeter square, then 1 cc volume of solution will show some conductance, that is nothing but specific conductance or conductivity. Is this clear, student? Yeah.
Yes, sir.
Yes, take 2. Yes. If L is equal to 1 unit length, A equal to 1 square unit length, right? Then you can define in a general manner. Suppose if you fix L equal to 1 centimeter, A equal to 1 centimeter square, then 1 cc volume solution will show some conductance, that is nothing but specific conductance. Okay, then okay, now we'll see what's the unit of specific conductance. So listen, students, so far I have introduced 3 terms, R, rho and kappa. I have introduced 3 terms. What is R? R is called resistance. The relation for R is directly proportional to L by A, or R is equal to rho into L by A. I gave this formula. Okay, and what is rho? Rho is called specific resistance, also called resistivity. Rho can be obtained by rearranging this expression. So rho is equal to R into A by L. A by L. And what is kappa? Kappa, by definition, mathematically we can say kappa is nothing but 1 by rho. Kappa is nothing but 1 by rho. Okay, so kappa is equal to, since rho is this, kappa is equal to R into, kappa is equal to 1 by rho, no? So if I substitute here, I'll get 1 by R into L by A. 1 by R is nothing but conductance, so I can also write this as G into L by A. Remember these formulas. These are all very important formulas. Okay, we are going to use often in the discussion. Take 2. Okay, now what is the unit of R? Unit of R? Ohm, right? Correct? Unit of R is ohm. What is the unit of rho? Ohm meter, very good. Unit of rho is ohm meter. What is the unit of G, conductance? Latest unit?
O.
Siemens, okay, Siemens. Latest unit is Siemens. What is the unit of kappa? See here, G unit is Siemens, L unit is meter, A unit is meter square. So kappa unit is Siemens meter inverse. Siemens meter inverse. I am giving you the units in SI unit, okay, under SI unit. Ohm, for R unit is ohm, rho unit is ohm meter, G unit is Siemens, and kappa unit is Siemens meter inverse. Okay, yeah. So remember all these informations. Now let me go to the next term that we are using here. Okay, so students, observe carefully. Suppose if I take a solution, this is very important, student. I'll take some solution and I'll immerse two electrodes. Such that I'll connect one to the negative terminal, the other to the positive terminal of the battery. Students, observe carefully. Now suppose if the distance between the two electrode is 1 centimeter and the area of cross section is 1 centimeter square, then the solution between the two electrodes, solution present between the two electrode, will give some conductance. What is that conductance called? L is equal to 1 centimeter, A equal to 1 centimeter square. Okay, then the solution present between the two electrode will give some conductance. What is that conductance? That is nothing but kappa, correct, student? That is nothing but kappa. What is the conductance of the whole solution? Whole solution will give some conductance. That is nothing but G, correct? Kappa is nothing but conductance offered by unit volume of solution or 1 cc volume of solution, whereas G is the conductance of the whole solution. So listen, so we can write, see this is conductance. Suppose if the volume between the two electrode is 1 cc, 1 cc volume solution, 1 cc volume solution or 1 cc solution shows a conductance which is kappa. Okay, what is the conductance of the whole solution? Suppose the total volume of the solution is V. So what is the conductance shown by VCC of the solution? Student, 1 cc means the solution which is present exactly between the two electrode. That solution will give some conductance, that is nothing but kappa. Okay, now my question is, what is the total conductance? If the volume of the entire volume of the solution is VCC, what is the total conductance? Which is nothing but kappa into V, correct? 1 cc solution gives this much conductance. Therefore, total conductance equal to, for V cc volume solution, will give kappa into V. So total conductance G is nothing but kappa into V. Am I right, student? Are you able to follow this? Yeah. This is kappa is conductance in conductance per unit volume. 1 cc volume, okay, into total volume of the solution will give total conductance. Simple. Now what I am going to do, so the next term that we are going to discuss is equivalent conductance. Take down, student. Equivalent conductance. Equivalent conductance. For this we use the symbol lambda EQ. Lambda EQ. EQ means equivalent conductance. Okay. What is the definition for equivalent conductance? Now what I am going to do, students, observe carefully. I will take some amount of water in a beaker. I will take some amount of water. Then I'll add 1 gram equivalent. Students, observe carefully. 1 gram equivalent of any electrolyte, of 1 gram equivalent of some electrolyte. Then the total conductance of this solution is nothing but equivalent conductance. Very simple. So you take some amount of water. You need not worry about whether we should take 100 ml water, 200 ml water, or 1 liter water. That is not important. Okay, you take any amount of water, any volume of water, add 1 gram equivalent of some electrolyte. Okay, then the total conductance of that solution is nothing but equivalent conductance. Okay, so I can write equivalent conductance equal to, I said equivalent conductance means total conductance. Okay, student, you know very well, total conductance G equal to kappa into V, right? Total conductance is nothing but kappa into V. So kappa into V, where V is the volume of the solution. V is the volume of the solution containing 1 gram equivalent of an electrolyte. Simple. Okay, V is the volume of the solution containing 1 gram equivalent of an electrolyte. Right? What is kappa? Kappa is the conductance offered by 1 cubic unit volume of solution, right? 1 cubic unit volume of solution, right? If you want total conductance, just multiply that with the volume of the total solution, right? Now, students, observe carefully. Here, what is meant by 1 gram equivalent? What is meant by 1 gram equivalent? Student, observe carefully. 1 gram equivalent is not 1 gram. Don't think that 1 gram equivalent means take 1 gram of the electrolyte and dissolve in water. No, that is wrong. What is 1 gram equivalent? 1 gram equivalent, okay, is nothing but equivalent mass of the electrolyte. It's nothing but equivalent mass of the electrolyte. Okay, right? Say for example, in the case of sodium chloride, what is the equivalent mass for sodium chloride? Sodium chloride is a salt. Sodium chloride is a salt which carry 1 positive charge. Okay, 1 molecule of sodium chloride carry 1 positive charge. So equivalent mass equal to, in the case of salt, equivalent mass of sodium chloride equal to molar mass of sodium chloride. This is the formula, divided by net positive charge present in 1 molecule. So 1 molecule of sodium chloride carry 1 positive charge, so divided by 1. Okay, so in the case of sodium chloride, equivalent mass, molar mass are equal. What is the molar mass of sodium chloride? Atomic mass of sodium is 23. Atomic mass of chlorine is 35.5. So the molar mass is 58.5 grams. 58.5 grams. So 1 gram equivalent of sodium chloride. Student, observe carefully. 1 gram equivalent of sodium chloride, okay, is equal to 58.5 gram of sodium chloride. Okay, so 1 gram equivalent means don't think that it is just 1 gram. No, 1 gram equivalent is nothing but equivalent mass of the electrolyte. In the case of sodium chloride, 1 gram equivalent is nothing but 58.5 grams. So you take 58.5 gram of sodium chloride and dissolve that sodium chloride in water. You will get a solution. Measure the conductance of that solution. Okay, that gives you the equivalent conductance of that solution. Okay, take note. So what is the definition for equivalent conductance? We can define simply like this. Equivalent conductance is the conductance of a solution is the conductance of a solution containing 1 gram equivalent of an electrolyte. Very simple. Equivalent conductance is conductance of a solution containing 1 gram equivalent of the electrolyte. But the thing you have to remember is 1 gram equivalent is not equal to 1 gram. 1 gram equivalent means it is the equivalent mass of the electrolyte. Okay, in the case of salt, you can find equivalent mass using this formula: molar mass divided by net positive charge present per molecule. Okay, for acids, for base, for oxidizing agent, reducing agent, we have different method of calculating equivalent mass. I am not going into the details of that. Okay, keep this in mind. Take down expression. So I'll give you the mathematical expression for equivalent conductance. Okay, students, observe carefully. Say for example, what is meant by normal? Say I'll take some solution. See, students, observe carefully. This is how I told you. You take some amount of water. In that you put 1 gram equivalent of some electrolyte. Okay, students, observe carefully. We don't know what is the volume of the water and all. So if I dissolve 1 gram equivalent of the electrolyte in water, I will get some normality. Okay, I will get some normality. So let the normality of the solution is N. Okay, so if N is the normality of the solution, suppose I'll take N is the normality of solution. Okay, students, observe carefully. What is meant by N normal solution? What is the meaning? N normal solution, what is the meaning? The meaning is this: 1000 cc or 1 liter, 1000 cc of the solution containing NING, sorry, 1000 cc of the solution containing 1 gram containing 1000 cc of solution containing N gram equivalents of electrolyte. Okay, student, keep this in mind. What is N? Suppose if a solution is given of some normality N. If the normality of the solution is N, what is the meaning for that? It means 1000 cc of the solution containing N gram equivalent of the electrolyte. Or I'll write in the other way: N gram equivalent of the electrolyte, N gram equivalent of the electrolyte I'll write like this: volume of, students, observe carefully, volume of N gram equivalent of electrolyte, volume of solution, volume of solution. One second, student, I'll write it neatly. Volume of solution containing N gram equivalent of electrolyte, N gram equivalent of electrolyte is equal to 1000, correct? 1000 cc. Okay, student, volume of solution containing, that's the meaning for normality. I am just rewriting the other way, that's all. 1000 cc contain N gram equivalent. So I am writing in the other way, that is volume of the solution containing N gram equivalent of electrolyte is 1000 cc. Now, what is the volume of the solution containing 1 gram equivalent of electrolyte? N gram is this. What is the volume of solution containing 1 gram equivalent of the electrolyte? Let me write to the next page. Students, I will go to the next page. So what is the volume of solution? Volume of solution containing 1 gram equivalent of electrolyte. That is nothing but 1000 by n. 1000 by n. Okay. Now you know very well, total conductance G is nothing but kappa into V, correct? Kappa into V. If the volume of the solution contain 1 gram equivalent of electrolyte, it is nothing but, then the conductance become equivalent conductance. So equivalent conductance equal to kappa into, in the place of V, I'll put this 1000 by normality. So this is the formula for equivalent conductance, students. Note down. Equivalent conductance equal to 1000 kappa by normality. Note down. 1000 kappa by normality of the solution. Formula for equivalent conductance. Okay. Now what is the unit? Unit of equivalent conductance, let me write here. Unit of equivalent conductance is, see, the unit of kappa here is Siemens centimeter inverse, because I defined that 1 cc volume solution shows a conductance of kappa. Okay, so there I mentioned that the distance between the two electrode is 1 centimeter and area of cross section is 1 centimeter square. Therefore, the unit of kappa is Siemens centimeter inverse, and divided by normality is there. Okay, what is the unit of normality? Yeah, what I missed one more thing. See here, student, I missed one more thing. See here, this is volume of solution, correct? Volume of the solution. Volume of solution is given in cc. Cc means centimeter cube. So unit of kappa is Siemens centimeter inverse, and the unit of this 1000 by normality is centimeter cube. Cc means centimeter cube, right? And the solution contain 1 gram equivalent of electrolyte. So I'll put gram equivalent whole inverse. So if you simplify this, you'll get Siemens centimeter square gram equivalent whole inverse. This is the unit of equivalent conductance. Students, are you able to follow this? Very simple. See, the unit of kappa is Siemens centimeter inverse, that we know already. 1000 by n is nothing but volume, correct? 1000 by n is nothing but volume. Volume is given in the unit of cc. Cc means centimeter cube. So Siemens centimeter inverse is the unit of kappa. Centimeter cube is the volume unit, and solution contain 1 gram equivalent, right? So gram equivalent whole inverse. If you simplify this, you'll get this unit. This is nothing but the unit of equivalent conductance. Okay, but student, remember, we are not using equivalent conductance, okay, in our books. So we are going to focus mainly on molar conductance. I'm going to introduce that next. So equivalent conductance is nothing but 1000 kappa by n, right? For competitive examination, okay, you should remember this expression. Now I'll give one more information here. Student, observe carefully. If kappa is measured in Siemens centimeter inverse, if kappa value is given in Siemens centimeter inverse, then the formula for equivalent conductance is 1000 into kappa by normality. Sometime in the examination they'll give kappa in Siemens meter inverse unit. Student, observe carefully. If kappa is given in Siemens meter inverse unit, then equivalent conductance you have to calculate by using this formula, kappa by 1000 into normality. That 1000 will come down. Note down. Right now, What is the SI unit? SI unit of equivalent conductance. Right? Siemens, instead of centimeter square, you put meter square, that's all. Siemens meter square, gram equivalent whole inverse. Siemens meter square, gram equivalent whole inverse. That is the SI unit of equivalent conductance. Okay, take note. And this formula, remember students, these two formulas are very important. So the next term that I am going to introduce is molar conductance, which is actually available in the book. Equivalent conductance is not there, but molar conductance is available. So what is molar conductance? Molar conductance, okay, which we represent by the symbol lambda m. Okay, lambda m. Students, observe carefully. This symbol we call it as big lambda, and this is small lambda. We use big lambda symbol for whole electrolyte, and small lambda symbol for ions. Okay, if you want to give equivalent conductance of ion, use small lambda. If you want to give equivalent conductance of an electrolyte, then use a big lambda symbol. Okay, but both have same meaning. Both are equivalent conductance or molar conductance. Right? Now, what is molar conductance? What is the definition? Students, observe carefully. Let me take a vessel with some amount of water. Okay, you take some amount of water in a beaker or in a vessel. Then dissolve 1 mole of an electrolyte. 1 mole. 1 mole of electrolyte, and measure the total conductance of that solution. See, if you dissolve 1 mole of electrolyte in water, you will get a solution, right? Measure the whole conductance, total conductance of the solution. Okay, that is nothing but molar conductance of that solution. Okay, so you know very well the formula for whole conductance, total conductance is kappa G equal to kappa into V. Suppose I'll keep the kappa as such. If V contain volume of, if V is volume of solution containing 1 mole of an electrolyte. Okay, if volume of solution contain 1 mole of electrolyte, then this G is given as symbol lambda m. If you don't put 1 mole, if you put some other mole, 0.5 mole or 0.1 mole, then it is not equivalent conductance. Molar conductance. What is molar conductance? Molar conductance is nothing but kappa into V, where V is the volume of the solution containing 1 mole of electrolyte. Are you able to follow, student? Is this clear?
Yes, sir.
Yes, take down. So what is molar conductance? What's the definition? Let me write the definition next page. So what is molar conductance? What is the definition? So molar conductance of a solution, molar conductance of a solution is the conductance of the solution containing, okay, molar conductance of a solution is the conductance of the solution containing 1 mole of the electrolyte. 1 mole of an electrolyte. Okay, take down. You should put 1 mole. If the solution contain 1 mole of electrolyte, then the conductance of that solution is nothing but equivalent conductance of the solution. I'm very sorry, molar conductance of the solution. I'm sorry, because we are adding 1 mole. So if you add 1 mole of electrolyte, then the conductance is called molar conductance. Simple. Okay, now let me give the expression for mathematical expression for molar conductance. Students, observe carefully. So molar conductance lambda m equal to kappa into V I said. Okay, now listen, let me focus on this V. Suppose, students, observe carefully, I'll take some amount of water, I'll put 1 mole of some electrolyte, 1 mole. See, I didn't mention anything about the water, volume of water. Volume of water may be 100 ml, 200 ml, 1 liter, whatever maybe it is. If I dissolve 1 mole of electrolyte in water, in some amount of water, I'll get a solution. Let the volume of the solution be m. I'm sorry, molarity. Let the molarity of the solution is m. In the previous case, I used normality because we have dissolved 1 gram equivalent. So that will give you normality. Now I am dissolving 1 mole of electrolyte. If I dissolve 1 mole of electrolyte in water, we will get a solution with some molarity. Let it be m. Okay, so suppose if m is the molarity of the solution, m is the molarity of the solution. Molarity of the solution. What is the meaning for molarity? Very simple. Molarity means m moles of electrolyte, or I'll write as before. Molarity of solution. What is the meaning? The meaning is 1000 cc of the solution, or 1 liter. 1000 cc of the solution containing 1 mole of electrolyte. 1000 cc of solution containing 1 mole of electrolyte. That's the meaning for molarity. I'm sorry, m mole of electrolyte, m, because I took molarity as m here. Okay, students, observe carefully. If I say a solution has m molarity, what is the meaning? 1000 cc of the solution containing m mole of the electrolyte. Or I will just rearrange this statement like this. See, volume of solution containing m mole of electrolyte. Volume of solution containing m mole of electrolyte equal to 1000 cc, 1000 centimeter cube. Correct? If I say molarity is m, then m mole of electrolyte must present in 1000 cc volume. Okay, what is the volume of solution containing 1 mole of electrolyte? If m mole is 1000 cc, for 1 mole what is the volume? Okay, let me write in the next page. So it's nothing but 1000 by m, correct? So volume of solution containing 1 mole of electrolyte is equal to 1000 by m centimeter cube. 1000 by m centimeter cube. This is the volume of the solution containing 1 mole of electrolyte. And what is molar conductance? As I told you before, molar conductance is nothing but kappa into volume of the solution containing 1 mole of electrolyte. Correct, student? Kappa into volume of the solution containing 1 mole of electrolyte. So volume of the solution containing 1 mole of electrolyte is 1000 by molarity. So I can write this as kappa into, I'll keep kappa as such. In the place of volume, I'll put this one, 1000 by m. Okay, so molar conductance is nothing but 1000 into kappa by molarity of the solution. 1000 into kappa by molarity of the solution. Okay, what is the unit of kappa? Unit of molar conductance. Let me write here. Unit of molar conductance. Unit of kappa. Suppose if unit of kappa is given in Siemens centimeter inverse. Okay, this is the unit of kappa unit. Then 1000 by m is nothing but volume, right? 1000 by m is nothing but volume. Volume unit is centimeter cube. And solution containing 1 mole of electrolyte, therefore per mole. Mole inverse, I'll put mole inverse. So if I simplify this, I'll get Siemens centimeter square per mole. This is the unit of molar conductance. Is this clear, student? So the formula is this. If, remember this formula, if kappa is given in Siemens centimeter inverse, then molar conductance can be calculated using the formula 1000 kappa by molarity. Okay, in this case the unit of molar conductance is Siemens centimeter square per mole. Sometime in the examination, sometime they'll give kappa in Siemens meter inverse. If kappa is given in Siemens meter inverse, then molar conductance should be calculated using the formula kappa by 1000 into molarity. By 1000 into molarity. So if kappa is given in Siemens meter inverse, then the unit of molar conductance in this case is Siemens meter square per mole. Meter square per mole. And this is the SI unit. You know very well. This is the SI unit. Okay.